Welcome back. So we're talking about mining ore or mining mineral resources out of the ground. We don't just dig anywhere for something of value, right? We look for clues in certain spots because we're looking for where these resources are concentrated, right? If I wanted to dig for diamonds, if I really wanted to mine for diamonds, I'm not going to just start digging in my backyard. There's no diamonds there. I want to go to where they're concentrated. I might have to go to a place like, for instance, South Africa or northern Canada, where there are some diamond mines or diamond-rich areas. So, concentration is this idea of looking for stuff where there's a lot of it, where it's concentrated. So in general, the higher the concentration of the substance, the more economical it is to mine. The more of it in a certain area, the more you're going to make. Right? The less of it, the less you're going to make. Different materials are worth different amounts. So you kind of want to play around with different concentrations for different minerals. So economics is what controls the grade or concentration of a substance that makes the deposit profitable to mine. For example, gold might be worth something one day, and then there's something weird happens and gold is only worth half as much it was the next day. Well, it might not be profitable enough to mine out anymore because of the fluctuation of prices. So the economics drives the prices of these things. Sometimes they're more profitable, sometimes they're less profitable. But because each source has a different value, different substances require different concentrations to be profitable. For instance, gold is much more expensive than copper. So you're gonna, depending on how much money you make, the concentrations you need for these to be in the ground are typically going to be different. But again, the concentration changes due to economic conditions such as demand for the substance, cost of extraction, etc., etc., etc. Let's look at an example: copper. So from 1880, so this chart looks at year versus percent copper in economic deposits. So how much of the material that we're pulling out of the ground, what percentage of it is copper? So from 1880 to about 1960, the grade of copper ore showed a steady decrease from about 3% down to less than 1%, mainly due to increased efficiency in mining. So mining became more efficient, meaning you're spending less money on it, so your cost of extracting it is dropping. Therefore, the percent concentration didn't have to be so high. All right, so when you spend a lot of money, the concentration of the material has to be high because what you're extracting out of the ground has to make you a lot of money. Whereas if you become more efficient, it's costing you less. Obviously, you would still want to find the higher percentage deposit, but you could still kind of bring that a little bit down and still make money. So you could still find an area that maybe has less of a concentration of material in it and still be profitable. That was until, again, about 1960. And then from 1960 to 1980, the grade increased to over 1% due to increasing cost of energy and abundant supply produced by cheaper labor in other countries. So energy, and that actually continues into the 2000s. So it shot up because, well, energy costs more, electricity costs more, fuel costs more, as time goes on. But also, different countries were producing it more cheaply, so therefore we need a higher percentage for it to be more profitable because of certain factors. So the concentration that you need to mine out of different materials changes. And again, these are just some copper ores. This blue is called azurite, chemically contains copper. We have boronite, chemically contains copper. We have chrysocolla, this green stuff, chemically contains copper. Looks like a little bit of malachite here, chemically contains copper. We don't see big chunks of copper like what we see in this native copper here. So copper is embedded chemically in these things. We have to, extract it out. Hopefully it has a high enough concentration. Another example is gold. So gold prices vary on a daily basis. Same with a lot of other minerals, but gold is a very famous one. When gold prices are high, all right, old abandoned mines that were closed tend to reopen. because, you know, maybe the mines closed because it was just too hard. It cost too much to mine out that gold. The concentration of the gold in the rocks in that ore you're pulling out was real low. But when gold prices go up, well, it makes that mine that was previously closed, well, okay, even though it's going to cost a little bit more, we're still going to make money because gold prices are so high. But when prices drop, mines close. So sometimes it fluctuates daily. Mine might be open one day, it might be closed the next day. The cost of labor is currently so high in the U.S. for mining that few gold mines can operate profitably. That's why, you know, think back to that map at the beginning in the first video of Arizona. There's really only a couple major gold mines. It's just because it's so hard to profit from it. It has to, it's very rare. So you have to find really good concentration deposits, really big deposits for it to be even worthwhile. But in third world countries where labor costs are really low, where they don't pay people a lot, gold mines that have ore concentrations well below those found in the U.S. can operate with a profit because you're spending less money to extract it. Therefore, even though you're making less, you're still making a profit because of how low the labor costs are. Again, when we're extracting gold from the ground, it's not big chunks of gold. That's not how gold comes out. It's embedded in the rock. This is actually a high amount of gold concentrated in this rock. That's a lot of gold. You know, even though it's little flakes, and by the time you crush this and extract it out, it might just be just a little pinch of it. Well, gold's pretty expensive, but that's still just one little rock. More so, it looks like this. Can you see any gold in here? No. It's chemically in there. You have to crush it, chemical process, heat it up, melt it, extract it. You have to do all sorts of things. So there's gold in there. For instance, 0.116 ounces per ton. So in every ton, that means every ton of rocks, every 2,000 pounds of rocks you take out, there's 0.1 ounce. I don't know if you know how much 0.1 ounce of gold is, but you know, that's less. That's, you know, a few grains of sand. You know, it's a few grains of sand. It's not much. It's not much. All right, but you know, you do that. You know, that's just 1 ton. But if you're processing thousands of tons of rock a day, well, you're actually going to make some money off of that. Again, another example of copper or of gold ore. Again, you can't really see it in here. It's in there. All right. A lot of times, gold can be found with the mineral quartz. That's the mineral quartz here. You see the mineral quartz over here. It looks like little quartzes over here. Just because you have quartz doesn't mean you have gold. But a lot of times, you do find gold. If you do find gold, it's somewhere with quartz. So here's the price of gold over the past 30 years. From the early 90s, where it was about $300 per ounce, whereas when this was done, the last close was $1,848 per ounce. So that's an increase of over 420% over the past 30 years when this was taken. So the price of gold fluctuates. It fluctuates. So when we're talking about extracting this stuff and the concentration, we're looking at a number called a concentration factor. For every substance that we mine out of the ground, we can determine the concentration necessary for it to be profitable to mine out. So again, the more stuff there is of what we're looking for in a certain area, the higher the concentration, the less stuff there is in the rocks we're looking at, the lower the concentration. Depending on the economics, each different mineral resource has a different number called a concentration factor. So by dividing the economical concentration by the average crustal abundance for that substance, we can determine, again, a value called the concentration factor. So we can look at, you know, how much of this stuff is, on average, in the crust of the earth around the world. However, how much, what does it need to be? How much more than the average crustal abundance does it need to be in order to be profitable to mine out? Which varies from which varies in time, which varies from place to place. So let's do an example, all right, for aluminum. Aluminum, which has a crustal abundance of 8%. That means when we're looking at the crust of the earth, on average, and all the rocks and minerals, about 8% of the crust of the earth contains aluminum. All right? So, that's on average. But aluminum has a concentration factor of 3 to 4, which means that an economic deposit of aluminum must contain between 3 and 4 times more concentration than the average crustal abundance. So in order for aluminum to be worthwhile to take out of the ground, an area, it has to have 3 to 4 times the aluminum in the rocks in the ground than it does on average around the earth. Right? So we can't just dig anywhere for aluminum. We're trying to find a place that has at least 3 to 4 times the concentration of the normal crust of the earth. So therefore, if the average percent of aluminum in the crust of the earth is 8%, and we need 3 to 4 times more of that, so 8 times 3 is 24, 8 times 4 is 32. So we're looking for an area kind of at least with a minimum between 24 and 32% aluminum to be economical. So we take a rock, we break it down, we do some fancy, we have a metallurgist look at some fancy stuff, use some fancy equipment, and say, oh, in this rock, 30% of this rock is aluminum. So this would be a good site to dig this stuff out. So this would be a good site for aluminum ore. So that's an example. So different substances have different abundance in the crust and different concentration factors in order to be viable. For instance, gold. Gold is very rare. It only, on average, exists in the crust in about 0.000002%, so it's not very common. So we need a concentration factor of 4,000 to 5,000 to make it economically viable. All right. Copper, 0.0058%. That's on average how much copper, if we take any random rock, on average around the earth, it contains 0.0058% copper, which is not economically viable. An area would have to have a concentration factor of 100 to 200 at least in order for that area to be economically viable. So you do some math. You take this number, multiply it by that. That's the percentage you're looking for, right? That's the percentage you're looking for. All right, for instance, titanium, 0.86% average crustal abundance, right? But it needs a concentration factor of 25 to 100. So let's just do the high end of that. So 0.86% times 100, move the decimal point 2 spots. So in order for a substance to be economically viable to extract titanium from it, it has to have upwards of 86% of that stuff has to be titanium. Different substances have different concentration factors, the amount needed to be economically viable. If you find, for instance, zinc, if you find a rock that doesn't contain 300 times more the average crustal abundance, it only contains 100 times more zinc than the average crustal abundance. Well, that's a lot. It's more than the average around the world, but it's not enough to be economically viable to pull out. All right, so a little bit of math is involved. Please remember. So let's go ahead and pause there. So when we come back, we'll talk about, well, where does all this stuff come from? How does it get there? How does copper and gold and how does all this stuff get where it is for us to mine it out? So we'll pause here and I'll see you back here in just a second.